Hope this is okay for everybody.
Yeah, can see it.
So today I would like to have a second talk about the Intel Inspector. So Intel Inspector is probably does not have the attention as vTune at Intel, but we have lots of customers who like to use this tool, especially for the threading analysis and partially for the memory analysis. And we now have also some GPU functionality in it. So I know that Rolf Rabenseifner from HLRS is doing regular presentation or lectures about using Inspector, even at the Jülich Compute Center. So there are some people who like this tool, and it has a long history, and it's very useful for checking correctness of codes in memory, and especially the threading analysis is very nice. So I would like to give a little introduction to Inspector, and who wants to do something hands-on can use the playbook available at this page. Sorry, this is not in the original presentation where you have the PDF, but the same location as the playbook for vTune. And sorry for the confusion, because the source code I laid there was meant only for this Inspector presentation, or for the playbook with Inspector, because it's a spoiled source code where one false line is introduced just to have something shown in an Inspector. So next would be another overview slide about how it looks like. So when you've done the analysis, either by using the GUI or by using the command line and then loading the results into the GUI, you see a list of errors that Inspector finds, but please be warned, because there is a giant number of false positives shown. So it's probably good to ignore at first sight all issues that are shown in libraries, and just concentrate on issues that are directly found in your source code. So might be also issues with our libraries, but hope that most of them are really false positives. And it's in principle simple to use, because you don't have to recompile. You can just take your executable built by any compiler, and even inspect third-party libraries. But it's better if you compile it with debugging information, because then you have the correct source lines or code snippets available. So that's a better usage here. So how to start from the GUI. So you open the GUI, and you can, on the left side, you can select. You can select an. Hello?
It's Shaylin who's not on mute.
You can select the analysis type. And normally there are two classes of analysis. One is the memory analysis, and one is the threading analysis. And for each class, there are 3 levels of severity. And as you can imagine, the more in-deep analysis you are using, the more overhead you see. And sometimes the overhead is really, really huge, but the good message is that you can select a minimal workload. So it does not, in contrast to performance profiling, it's not necessary to give real workload here, but it's probably you need a workload that touches all um, the regions of your code, but the smallest available. So it does not even report errors that really happen during your source runs, like race conditions. So in some cases, race conditions turn out sometimes only in some strange configurations, or not always. But this the way this tool works is to simulate all kinds of memory accesses for the threading analysis. And so it will find even errors that are not happening in your special run, but could potentially happen in another run. So this is very, very nice because it can help you to avoid errors that doesn't happen for probably small workloads, but will happen then for larger workloads or vice versa. So the command line interface is easy. So you have the command line tool version of inspector, this xe-cl. Minus C is minus collect, and ME3 is the toughest memory inspection. And for threading is TI3 is the most involved threading um, um, threading analysis. And view results you can do with minus report equals problems and minus report all. It's probably not necessary. To open results in the GUI, you can open the GUI directly with the results folder. So how does a user interface look when you have generated results and then look at the problems? You see on the left upper side a list of problems. So often there are many more problems, and to focus on one, you can just click on the problem, and then you will see on the back code on the bottom code snippets and for the problem. So here, so people doing OpenMP will recognize this easily. So this is some code, some reduction in a critical region, or with the atomic pragma, and they just have commented the necessary pragma to enforce such a race condition. And so just to force an error here, but in real life, you should get an error report when you have a source code with OpenMP, for example, and maybe you have a huge loop and have to privatize certain variables, and you forgot a privatized variable, then this tool should show you this variable and recommends to make it private. Yeah, there are problem states, but I'm not doing much of this stuff like marking markings this problems. But maybe when you really want to do an in-depth analysis with real code, it's necessary that you filter out first all things that you have identified as false positives to concentrate on the real errors, or when you have agreed that one version is clean, then you can all filter out all false positives, and for the upcoming tests then concentrate on the new errors. So when you have a problem and you double click on it, like in VTune, this another window with the source code opens. And when this is a threading problem with different threads, then at least two windows will open and show the critical source code. So here in this, it is just the this critical region that was commented out, and you see it for both threads. But it could be also when it's a memory problem, then it could show on one window the allocation side, and on the other window where this array is used and the memory is violated. So this is possible and quite handy. And we have new offload features. And yeah, I'm not sure if I really should recommend to use it now. Maybe if you want to try, but I found it very hard to use it. But for the one feature I was trying, it was delivering the right results. So the one that you see in the playbook. So what can it see or detect? So here are three modes. Native is just the usual usage on the host. And CPU offload is that you use, for example, SQL code, but you don't run it on the GPU, but instead of it, run it on the CPU. So the SPIR-V intermediate source code is generated but executed on the CPU. And the last native offload is that you have this OpenMP offloading, but you force by environment variable the system to execute it on the host. So this is for inspector far more easy to inspect this stuff on the host CPU than going to the GPU, as you can imagine. And you see in this matrix which kind of errors are supported and which not. So for CPU offload, there's a lot of unsupported stuff. I must admit that this presentation is, or this information is probably half a year old, and maybe they made some progress on it and we have now more features integrated. So how to run it and to force it running on the CPU. So we choose the OpenCL version, but running on the CPU, and you can use it by the variable SQL device filter equals OpenCL : CPU. That will force the execution to run on your CPU with the OpenCL backend. So don't know if this would be, probably wouldn't be working with level 0. I haven't tried. But following these instructions here, using the OpenCL backend. Yeah, and for OpenMP offloading, you can force, on the one hand, to do OpenMP offloading, make it mandatory, but on the other side, you choose as the offload target the CPU. So the code is doing the same as for the GPU offloading, but it runs on the CPU because this is easier for inspector to get the diagnostics done on the CPU, as you can imagine. And the last one, I didn't use the clconfig use vectorizer for JITted code, so probably I should also try it. Yeah, and the general rule is to use a minimal workload, and you can then use the GUI or the command line interface to check for the results. So one application example would be to use to allocate memory on the host or host device, and inside the queue you use the host pointer for the results, even though it's only allocated for the CPU, for the host. So that should be, at least for the GPU execution, that should result in an error. On the CPU execution, it could work, but inspector should show us results. These are results shown on the left side. You see how it runs without inspector, and it shows the elapsed time, for example, 4.8 or 4.9 seconds, say. And on the right side, you see the inspector analysis with the most involved memory inspection, and you see it's reporting that it's running on the host, but with the PRV interface. So it's a GPU code in principle running on the host. And you see that the runtime goes now from roughly 5 seconds to over 116 seconds. So there is a huge overhead. And you see it finds 83 problems, and probably 82 of them are just false positives, and only the yellow one with the special special detection line here is showing a real error, and that is the wrong host pointer, that the host pointer is used on the device. So this is a little bit frustrating that there are so many false positives, but the opposite would be that they could probably lose some real problems, so that we don't see the real positives and have false, so to say, false negatives, and that would be probably worse. And people are working, the developers, on making this more functioning in a better way. So ignoring all these false positives. But my advice would be to focus on the issues that are clearly detected on your source code and not in the libraries. So how does it look like in the GUI? So unfortunately, for my example, it didn't work out. It can probably be that some of the code was optimized away, or optimized in a way that it couldn't be shown anymore in source code. So that's to the example that I provided in the playbook. And well, here's something about that they are learning from the customers. So they would like to work with customers and to optimize that. And now I would like to to make a little demo and to show how it's working. So sorry for the confusion with the VTune playbook. I was okay. So maybe I should do it as Klaus Dieter and use an Jupyter notebook. Here, that's quite smart. So it's I was just using single windows. So I built my n-body code already, and I was using out of the directory from this morning a changed source code for the gsimulation.cpp. So you could now just do a diff between my broken version and the original version to see immediately what has changed. But let's do it with inspector, if inspector can be also as smart as you to find the right line where something happens without seeing the original. So I built here my code and I can run it first. Let's see if I have already said it. Maybe it's smarter to do this in one line. No. So I just run the broken code here, src, and it fails here with an error message that we have done something wrong. So next step would be to set the environment variables. So we first force the execution to use this OpenCL backend, and we use the CPU device. And the second would be that we exporting the CirclePy trace. So the CirclePy trace shows the backend calls. And I learned that you can, when you add or use 2 or -1, then you see even more, or for each call to a backend call, you see it on the command line. And when you set then ZE_debug, you see even the level 0 calls that belong to this backend call. So this gives you a lot of information, but probably confusing for the beginning. So we just use =1 to have a basic, the basic information, and then we run it again. And now it is running and even providing results. And it says that it's using libopencl, and the selected platform is now the CPU here and not the GPU. So so that was my. So I was just using one step here instead of 10 steps as the default. So I changed the default, which is not necessary because you can do this with command line variables. So I will now try to run inspector with the minimal size of particles, just with 160 particles, because this will take very long. Oops, same error as this morning. So now it starts, and it will take some time. So in the meantime, I can go on talking, and I would suggest that you probably wait for the it even wants to do me smaller. Oh, it says it has only detected one problem. So this is strange. I've expected something else, but probably this is due because I was doing the first experiment um, on a Gen 9 GPU, and now this is a DG1 GPU. Maybe it makes a difference if it's integrated graphics that shares the some of the memory with the CPU in contrast to the discrete GPU with its own memory. So let's see. I would recommend doing this again on a Gen 9 because then it will show you something like the error message that we saw in the presentation. I put it here. So this is would be normally be seen here, and you can now just inspect this by maybe the application of this analysis ended premature here because of these problems printed out before, which does not happen on the Gen 9 GPU. So let's try what if it has some report. So this is clearly wrong. So it shows us some issues in the standard C++ library. So this is very probably um, a false positive. But when you do this on Gen 9, you see this here. You see it's even it's a very experimental uh, branch of the tool here, and I probably have to get more in contact with the developers to get more information. But when it's ready, I think it will give you good information here for your analysis. And let's go. So on Gen 9, it was pointing me on an issue with the host pointer on line number 120. So let's just open the code and go to line. Oh, sorry, that's not 120. And you see that I did the same naughty stuff as before, my colleagues. I just commented out something. So the energy that is reduced here for this simulation is done on the malloc shared pointer in USM, and you can do a reduction on the energy variable, but yeah, and it is then copied back to the host. And here I just used an ordinary pointer on the host to enforce an error. So this couldn't work on the device and will produce an error. And you see the GPU implementation crashed, and well, maybe on the CPU it's in the same memory space, so it doesn't matter. So I think that's all of it. And you see you've got some more information in the backup of the presentation. When you try the inspector experiment with my playbook, please choose a Gen 9 GPU. So you can figure it out by the first talk of Klaus Dieter, how to distinguish between this Iris Max. So you have the can use Gen 9 to specify going on a Gen 9 GPU and do the experiment again. That will lead to the outcome that's documented in the playbook. Do you have more? I haven't looked at the. Oh, there's nothing in the chat. Do you have more questions? Otherwise, I would thank you and go to the